Sir, are you saying something?
So, in the previous class, uh, some of the participants were of the view that we shall go through the question answer section of the course material. So, let us have a look over your course material. So, this is your course material as shown in the screen, and this is Unit 3 complex variable. So, we are discussing analyticity, and you can see in the screen. Is it visible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So this is the plane, Argand plane, which I was explaining you in the previous class, and this is in polar coordinate system r and theta, and the Euler form, that is the exponential form of representing a trigonometric function. Then complex analytic function in term of u and iv, which I was discussing in the previous class. Then there are some doubts regarding your domain and range by some of the students, and this is there in your syllabus, your course material, where they have explained what Z0 actually is and what is the neighborhood and how this neighborhood how in this neighborhood is there in the domain of that domain of those points or the function. Okay, this then if we approach from different from x axis or y axis, how z del z takes the form which I was discussing in the previous class. Then your Cauchy-Riemann condition and the
Sir, sir,
is it visible?
sir. Yes, sir. But sir, I only discuss the SAQ and TQ that are available.
हाँ वो आगे आएंगे ना, जब खत्म हो जाएगा कोर्स स्क्रीन, जब
Okay,
यूनिट
sir.
खत्म हो जाएगा, then we shall have those things. So
Okay, sir.
then your final expression is in the form this one, del u by del x, del v by del y, which is 2x, and del u by del y and del v by del y, which I was the previous class with giving an example. Okay. This is the Cauchy-Riemann condition. Then we have discussed the harmonic function yesterday. Then we are concerned about these things. Example. So if u is equal to 2x 1 minus y, so it is harmonic in some domain, but our concern is to have your. So see, here they have evaluated your del u by del x, and which is equal to del v by del y is equal to 2 1 minus y. Similarly, your del u by del y is equal to minus del v by del x is equal to minus 2x. So it obeys the Cauchy-Riemann condition and it is analytic. Then in here by integrating you will have final term 2z plus iz square is the uh, uh, harmonic conjugate of V. Okay. Then SAQ, obtain the analytic function whose real part is the exponents e to the power x cos y. So your u is equal to cos y. If u is equal to cos y, then you can have your del u by del x, and this is nothing but del v by del y. So del v by del y is equal to e to the power x cos x. From that you can have your v by integrating integration ex cos y dy del y or dy. And if you have your u and v, you can have the function u plus I v. Okay, SAQ2. Then some elementary complex functions. I have explained you yesterday, exponential function, trigonometric, hyperbolic, all those I have explained you, but here it is only exponential function. Then there is another example, derivative of dz e to the power z is equal to ez. You have to show. So your ez is nothing but e to the power x plus iy, because z is a complex number represented by x plus iy. So e to the power x plus iy is equal to e to the power x multiplied by e to the power iy. In exponential function, e to the power x plus y is equal to e to the power x into x to e to the power y. So your this is not e to the power x cos y plus I sin y, because cos y plus I sin y is equal to e to the power I theta. Cos theta plus I sin theta is equal to e to the power I theta. So cos y plus I sin y is equal to e to the power iy. So your u plus I v. So your u is equal to e to the power x cos y and v is equal to e to the power x sin y. Then your f is f dash is equal to del u by del x plus I del v by del x. So your del u by del x is equal to e to the power x cos y and del v by del x is equal to e to the power x sin y. And your f dash is equal to integrating the original function, that is your e to the power x plus iy or e to the power x cos y plus I sin y. You can have your e to the power z. Okay. So this is example 10 to the power 10.3. Then your trigonometric function, then your hyperbolic function, then your branch cut, ये सब पढ़ा आपको देखो, logarithmic function, gamma function. Okay, for all those, then it is SAQ6. Obtain the values of gamma function, gamma 3 by 2 and gamma 5 by 2, and the value of gamma minus half. So you know how your gamma function is evaluated from the integral integration 0 to infinite t to the power z e to the power minus z dt, and there is a standard table from where you can have your values of gamma function e to the power half, gamma 3 by 2, gamma 5 by 2, so on and so forth. Okay. Then your self-assessment questions. These are worked out in your course material. Fz is equal to z dot z star, where z star is the complex conjugate of z, and you can have your f dash z and other things from those. Okay. Then there are some terminal questions about derivative and your polar form. Okay, this is unit 1. Next is your complex integration. Before going to complex integration, I shall discuss some basic concepts, okay, which are there in the syllabus, and I shall show you in my course material. Cauchy integral theorem, then your consequence of Cauchy integral theorem, Cauchy integral formula, then worked out problems, so on and so forth. Then your Lorentz series, Taylor series, how they can be solved by using complex integration. Then your residue theorem, and how to evaluate residue by using this. Okay. So this is all about your unit 3. And these are the worked out examples. Okay. So these 3 part constitute your complex variable course in your mathematical physics.
Sir, in one book we have two blocks, one block 1 and block 2. What they mean?
Hmm? These are different parts of the course. Okay.
The whole syllabus is divided into two blocks.
The whole syllabus is arranged in 4 blocks.
Oh,
Five
This is
blocks actually.
I have 5 blocks in mathematical physics. For different courses, it is different. For mathematical physics, it is 5 blocks. So you have come across the whole course material. So let us now have your complex integration part. So before that, let us discuss some concepts. Is the screen visible?
yes, sir.
Yes, sir.
Okay. So in figure 4.1, there is a path, and in the path you come across different points: Z0, Z1, Z2, Zk minus 1, Zk, and Zn. And you have Zi1, Zi2, Zk, so on and so forth. And this is a line. So let us discuss line integral in a complex plane. The meaning of integration of a function of a real variable can be generalized to have the definition of the integral of a function of a complex variable, so in a manner shown here. So if fz be a function of the complex variable z, where z is equal to x plus iy in a region R, and C be a curve with endpoints A and B, you can see that in the line or in the curve, your initial point is small a and your terminal point is B. So the end point of the curve is A and B, and it is shown in a region R, and the curve can be represented as capital C. So let us assume that C is regular. The curve C is regular and can be described via parametrization. So parametrization means this can be represented in a algebraic format. So Z, which is a function of t, can be written as x plus iy, where x and y are function of t, and your t is greater or equal to ta and smaller equal to tb. T at A and T at B. So your T is a real parameter, and your xt and yt are real and single valued functions that have continuous first order derivatives. So our discussion will be valid if the curve C is piecewise regular. We now to prove it is piecewise regular, or to feel how it is piecewise regular, we have cut this curve into different parts. That is Z0, Z1, Z2, Zk minus 1, Zk, and Zn, and we can see that it is piecewise regular. Now you can divide the curve into n segments by introducing n plus 1 points: Z0, Z1, Z minus 1, Zn, so on and so forth. And your Z0 is coincident with A, and Zn is coincident with B. So your Zk be some point on the curve between Zk minus 1 and Zk Ck is equal to 1, 2 to n. So the product f of Zk, Zk minus 1, and summing over k, we can construct the sum in, and in will be summation k is equal to 1 to n, f of Zk minus 1 is equal to summation k is equal to 1 to n, f of Zk del Zk. So your del Zk is equal to Jk minus 1. Jk jk minus jk minus 1. You can see in the picture. Jk minus jk minus 1 is equal to jk. Z2 minus z1 is equal to z2. Z1 minus z0 is equal to z1. Are you getting it? So your I will be limit n tends to infinite in, which is nothing but limit n tends to infinite, modulus of del zk tends to 0, summation k is equal to 1 to n, f of jk del zk. So the limit exists and is independent of the choice of intermediate points, and if the manner in which the division is performed, then the right hand side of the equation represents the line integral, contour integral of f of z along the curve C, and can be written as integration C fz dz or integration a to b fz dz. So this can be represented as integration C f of z dz or integration a to b integration fz dz. Okay. So your integration over the contour fz dz is equal to limit n tends to infinite, del zk modulus tends to 0, summation k is equal to 1 to n, f of jk del zk. And this expression expresses a complex line integral as the limit of the sum. The value of the integral depends on fz and in general on the path connecting the endpoints a and b. So your complex line integral expressed as a sum of two real line integrals. Your z can be represented as x plus iy and fz can be represented as u plus iv. So your integration fz dz can be expressed as a sum of two real integrals in the following manner. Your del zk is equal to xk minus 1 plus iyk minus yk minus 1 is equal to del xk plus I del yk. And your f of jk is equal to u, which is a function of jk, and iv, which is a function, v is a function of jk. So your modulus of del zk tends to 0, and your modulus of del xk tends to 0, and modulus of del yk tends to 0. Now you can substitute all these things, and you can have your integration fz dz is equal to integrations over the contour u dx plus v minus v dy plus I integration over the contour v dx plus u dy. So your integration over the contour fz dz expressed as a definite integral. The parameterization of the curve C is expressed, and we can note that t increases from its initial value Ta to the final value Tb as we go along C from A to B. So by writing z is equal to zt, we can reduce the line integral to an ordinary integral with respect to parameter t. So it is a parametric equation. In the beginning I have told you. We can write dx and dy as dx is equal to x dot dt and dy is equal to y dot dt. Are you getting it? Okay.
Yes, sir.
So by substituting these in the original equation, you have your integration over the contour fz dz is equal to integration from ta to tb f of zt z dot dt. Z dot is equal to derivative of z. So here you assume that z dot is equal to dz by dt, and it is piecewise continuous on the interval t is greater than ta and smaller than tb. Now let us have a theorem. It is called Darbo's inequality, and I shown you this in the course material. Suppose fz is an analytic function and that fz is equal to df by dz is continuous in a region capital R. Then for contour C lying in R with endpoints A and B, your integration C fz dz is equal to f of A minus f of B. To prove this, you take integration over the contour fz dz is equal to integration over the contour df by dz dz, and this is nothing but f of B minus f of A. And your integration over the C fz dz and integration over minus C fz dz, there is a relation. The contour C traversed in the opposite direction. In the first case, the contour is traversed in a direction, and the second case in the opposite direction. 1 from A to B, and minus C is from B to A. So your integration over minus C fz dz is equal to obviously integration from minus TB to minus TA in the reverse format, f of z of minus t minus z dot of minus t dt. So z dot of minus t denotes the derivative of zt with respect to t evaluated at minus t. So by replacing minus t by t dash in the right hand side of the equation, we can obtain your integration minus c integration over minus c fz dz is equal to integration from ta to tb f of z t dash z dot t dash dt dash. And from that you can have your integration over minus c fz dz is equal to integration of c over c fz dz. So it is independent of the path. If you go from A to B, the result will be same as that if you go from B to A. And if you reverse the sense of integration, the sign of the value of the integral changes provided the path C with the end points is the same. So there are some properties you must remember. Integration over C k fz dz is equal to k integration C integration over C fz dz, where k is a constant. Similarly, your integration over C fz plus gz dz, where fz and dz are two different functions, is equal to integration over C fz dz plus integration over C gz dz. And if the points A, B, K are in C, then your integration from A to B fz dz is equal to integration from A to K fz dz plus integration from K to B fz dz. And another property is, if C is a continuous chain of contours C1, C2, so on and so forth, Ck, as shown in figure 4.2, your integration over C fz dz is equal to integration over C1 fz dz plus integration over C2 fz dz plus so on and so forth. And your modulus of complex line integral can be estimated from ML inequality, which is known as Darboux inequality, which is nothing but integration over C fz dz is smaller or equal to ML, is smaller or equal to ML, where M is a positive number and L is the length of the contour. So this is the derivation, very simple derivation. And you must understand these things. What is arc, what is simple arc, what is closed contour, curve, so on and so forth. So these are the definitions and the explanation, which will be very much helpful for you when you deal with complex integration. So what is an arc? In complex integration or complex variable course, your an arc C in the complex plane is a set of points Z, x, y such that x is equal to x of t and y is equal to y of t, and your plus t is smaller equal to t is smaller equal to t plus tb, where x and y are continuous functions of the real parameter t. So an arc is also called a curve. So A, B, C are different curves, and it can be represented, it can be said as arc, ARC. So what is a simple arc? A curve or arc C is simple if it does not intersect itself. So in these three, only A and only A is a simple arc. Simple your A and C are simple arc because in B the curve intersect at a point. So in simple arc, the curve do not intersect at any point, and your ZT1 is not equal to ZT2, and your T1 is not equal to T2 for T is smaller equal to T smaller equal to TP. And the simple arc is popularly known as Jordan arc, JORDAN ARC. So then what is a simple closed curve? A simple curve capital C for which Z of A is equal to Z of B is called a closed curve. And your figure 3 is a closed curve, where the end point and the start point meets at a point in the two-dimensional plane. So what is a smooth arc? An arc C is called a smooth arc if dz by dt exists everywhere on the arc and is continuous within the interval a b. Then what is a contour? Do you know all these things? Then we shall skip and go to next part. Am I audible?
Yes, sir.
Do you know these things? What is a contour? What is a smooth arc? What is a simple closed contour? Do you know these things?
Yes, sir.
You know? You are well acquainted with all this. What is a simply connected region? What is a multiply connected region? What is a cross cut? Anybody? Shall I explain these or move to the next part? Anybody? Am I audible?
Yes, sir.
हाँ तो क्या करना है? So if you know all these things, हाँ बताइए.
Sir, please explain this.
Okay, ठीक है. So then contour. A contour is an arc which consists of finite number of smooth arcs joined end to end. So what is a smooth arc? Smooth arc is such a arc where dz by dt exists everywhere on the arc and is continuous within the interval. So if you have a z and at all the points the first derivative exists in the interval, then it is a smooth arc. And if smooth arcs are joined at joined end to end, and it consists of a finite smooth arc are joined end to ends, and the number is finite. It is called a contour. A contour is an arc which consists of finite number of smooth arcs. Smooth arcs are those arcs where a first derivative exists in the interval, and the contour is the set of all these smooth arcs, or it consists all these finite number of smooth arcs joined end to end. Then what is a simple closed contour? A simple closed contour is called closed when the initial and final values coincide at some simple at some point. So a simple, look in the figure 4.5. So you can see that like 4.4, your 4.5, the curve is connected or joined at a point. So what is a connected region? A region R is called connected if any 2 points of the region can be connected by a curve which lies entirely within the region. So this is an important point. See in the figure 4.5. Okay. So there is a circle capital R and there is a curve C or capital C. So you can see that C is completely within R, and if you have a line inside C, all the points are there in R also. So any 2 points in the region can be connected by a curve, and that curve lies within the region. So suppose R is a circle and you have a point A and B. Here you are suppose see this is A point, this is B point, and when you connect this and this falls within R, then it is called a connected region. So simply connected region, if R is said to be simply connected, if any simple closed curve C which lies in R can be strung to a point without leaving R. So if you see here it is R. Is it visible? This is R. So you have a curve C. So if this curve is shrinked and in course of that truncation to a point say P, at any point it never goes outside that region R, then it is called a simply connected region. C को अगर हम क्या करेंगे, श्रिंक करेंगे, उसको ट्रंकेट करेंगे, तो कभी भी ये आर के बाहर नहीं जाएगा. सो योर दिस इज ए सिंपली कनेक्टेड रीजन. मल्टीपली कनेक्टेड रीजन क्या है? A region which is not simply connected is called a multiple connected region. You can see here. See, your C1, C2 and C3. There are three regions where which are in between in the middle of these three curves. All the points are not in R. So when you shrink a curve, some of the point falls in the interior region of either C1, C3 or C2, and which is not in R. So this is not a simply connected region. So crosscut. To make a multiply connected region to a simply connected region, use a crosscut. So if you connect a periphery of C1 to R and periphery of C2 to R, periphery of C3 to R, then these are called crosscuts. And by this way, your multiply connected region can be connected to a simply connected region. And these lines, your PQ or LM or RS, are known as crosscuts. Then convention regarding traversal of a closed path. So you can, this is an important thing. A boundary C of a region R is said to be traversed in positive sense or direction of an observer traveling in this direction and perpendicular to a plane has a region to the left. The positive direction is in counterclockwise direction. Counterclockwise, anti-clockwise direction is positive. Clockwise direction is negative. So you can see in figure 4.9, your if you come from origin through x-axis and C1 you arrived at 1, 1, it is positive. From 0 to 0 through 0, 1 you arrived at 1, 1. It is clockwise direction. It is negative. From 0, 0 through 1, 1 you come to 0, 1. It is counterclockwise. It is positive. Okay. Are you getting it?
Yes, sir.
Are you getting it?
Yes, sir.
Any doubt you can ask. So when you have a integration, you must understand these things well. Otherwise, the sign will be very much headache for you. पॉजिटिव नेगेटिव में आप इधर उधर होते रहेंगे और आउटपुट में गलत रिजल्ट आ जाएगा. ठीक है.
Are you getting it? Am I audible?
Yes,
Yes, sir. Yes, sir.
ठीक है. So there are some worked out examples you may try. Then Cauchy integral theorem. Cauchy integral theorem states that if a function fz is analytic at all points interior to a simply closed contour C, then integration over the closed contour C fz dz is equal to 0. Okay. So if there is a function fz which may be defined as u plus iv, where u is a function of x comma y and v is a function of x comma y, and your dz can be written as dx plus I dy. So if that function fz is analytic at all points interior to and on a simply closed contour C as shown in figure 4.12, then your integration over the closed contour fz dz is equal to 0. This is the statement of Cauchy integral theorem. And this theorem is very much important in complex variable theory. We provide an elementary proof of the theorem for a simply connected region. So let us let fz be a single valued and analytic function throughout a simply connected region. R and C be a closed path which lies entirely in R. In the complex plane, fz and dz can be written in the form fz is equal to u plus iv and dz is equal to dx plus dy. So your integration over the closed contour C fz dz is equal to integration over the closed contour u dx minus v dy plus I multiplied by integration over the closed contour v dx plus u dy, and this is derived from the expression integration over the closed contour u plus iv dx plus I dy. Since the function fz is analytic throughout the region capital R, the function u and v possess continuous partial derivatives of the first order in the region bounded by contour capital C. According to Green's theorem, which you know, in a plane, if P and Q, where P and Q are functions of x and y, x comma y are continuous and have continuous partial derivatives in a region capital R and on its boundary C, then your integration over the closed contour P dx plus Q dy is equal to integration del Q by del x minus del P by del y dx dy. You can refer Green's theorem to have this expression. So if you substitute this into our equation, integration over the closed contour P dx plus Q dy, and apply Cauchy-Riemann equation, that is del u by del y is equal to minus del v by del x. The second Cauchy-Riemann equation in Cartesian coordinate system, you have your integration over the closed contour u dx minus v dy is equal to minus of integration over r del v del x plus del u del y dx dy is equal to 0. Similarly, substituting P is equal to V and Q is equal to U in the equation and applying Cauchy-Riemann equation, the first Cauchy-Riemann equation, del U by del X is equal to del V by del Y, you have your integration over the closed contour C, V dx plus U dy is equal to integration R del U by del X minus del V by del Y dx dy is equal to 0. So you can substitute these in the original equation and you have your integration over the closed contour fz dz is equal to 0. Okay. So the theorem is thus proved. You substitute 4.18 and 4.19 in this equation, your 4.16, and you can have your integration over the closed contour fz dz is equal to 0 because these two terms will cancel out. One is minus of this, one is plus of this, and this will be 0. So this is the proof. Cauchy theorem establishes the fact that the integral of an analytic function over any closed contour lying entirely in a simply connected region is 0. It can also be shown that the theorem holds for multiply connected region. So in the consequence of Cauchy's theorem, we can discuss that if fz is analytic in a simply connected region, then integration from a to b fz dz is independent of the path joining the 2 points A and B in R. If you go from A to B in a path C1 and if you go to A to B in another path C2, A to B in a path C1 and A to B in another path C2, then the result will not change. Okay, so let us have the proof. So in figure 4.13, you have a closed path C. From A to B, a closed path. So that this can be having two parts, one from A to B through a path C2 and another is A to B through a path C1. Okay, and it encloses a region R. The circle encloses a region R. The point A and B lies on C. The path A to B via D is denoted by C1 and via E is denoted by C2. So by Cauchy theorem, your integration over the closed contour fz dz is equal to 0, or integration over the closed contour C1 fz dz is plus integration over the closed contour minus C2. See, here C2 is in anticlockwise direction, so you can write minus C. A to B जाएगा, B to A जब आएगा, so C2 का माइनस होगा, क्योंकि A to B है C2, so B to A होगा तो having a minus sign, so that is minus C2 fz dz 0 is equal to 0. So integration over the closed contour C1 fz dz minus of integration C2. अब वो माइनस C2 है, माइनस C2 को अगर हम C2 करेंगे so क्या होगा, your माइनस fz dz इंटीग्रेशन हो जाएगा, so that is nothing but 0. So your integration from C1 fz dz is equal to integration C2 fz dz. So it is path dependent. Line integral is path independent. Okay. So by this you can have your SAQs which was there in your syllabus. Let us discuss this. Okay. Is it visible now? Look. Am I audible?
Yes,
Yes,
sir.
sir.
Okay. So let us have your material. Cauchy integral theorem. These are the cross curves N3, N2, N4, N1, so on and so forth. Integration over C1 is equal to integration over C2. And the proof I have shown in the previous class. Here it is only the expression. Okay. And this is the Cauchy integral theorem which I have proved. Okay. Recently. SAQ, determine the domain over which the function given below are analytic. One is fz is equal to z square by z square plus 2, and fz is equal to sec hyperbolic z, and fz is equal to tan z using Cauchy theorem. And so that integration over the closed contour fz dz is equal to 0 where C is a closed contour. So how can you prove this? Anybody? Anybody? Is SAQ4 integration over C dz by z minus z0 is equal to 2 pi I, and your integration over C dz by z minus z0 to the power n is equal to 0. Okay. You can prove this by using this equation, this expression. Your integration over the closed contour fz dz is equal to 0. Okay. From that you can have these two. And your Cauchy integral formula, f of z0 is equal to 1 by 2 pi I integration over the closed contour fz dz z minus z0. If you want the proof, I can have this. If C is a circle, modulus of z is equal to pi. So g z0 is equal to integration over C 3z square minus 6 by z minus z0 dz. So you have to calculate g2. So Cauchy integral formula आप अगर यूज करेंगे, so your 1 by 2 pi I fz z minus z0 is equal to dz. You can see here your equation 11.18. So अब C is a circle having modulus pi. By now comparing the expression, you have your gz is equal to 2 pi I 3z square minus 6, and g2 is equal to 2 pi I 3 multiplied by 4. Your z is equal to 4 here, and minus 6 is equal to 12 pi I. Okay. Then show the geometric series converges for modulus of z smaller than 1 where a is a real number. So that series summation n is equal to 1 to infinite z to the power n 1 minus z converges for modulus of z smaller than 1, and find its sum, and the sum will be z. Then you prove that summation n is equal to 1 to infinite z to the power n minus 1 2 to the power n converges for modulus of z smaller than 2, and find its sum. Okay, so you know Taylor series and Lorentz series, and these are the SAQ. Write the Lorentz series expansion of e to the power z z minus 1 square about z is equal to 1, and determine the type of singularity and region of convergence. Okay. And these are the terminal questions. So go through this. If you have any doubt, you can ask in the next class. Okay.
Okay, sir.
Yes,
Yes,
sir.
sir.
Thank you. Thank you very much.
So
Thank you,
tomorrow
sir.
we'll have our class.
Tomorrow कितने बजे? 4 से 6 ले लेंगे?
5. Yes, sir.
4 से 6 ले लेते हैं, और ये वाला आपको कोशिश करो कल। अब हम कोशिश करते हैं कि डिफरेंशियल इक्वेशन का जो पार्ट आपको दिया है 2-3 दिन में आपने कुछ लोग कर लिया होगा. So we shall discuss those things.
Sir, सर लास्ट
ठीक
क्लास
है,
को वो एससीक्यू और टीक्यू थोड़ा डिस्कस कर लेंगे सर।
ठीक है। और डिफरेंशियल इक्वेशन वाला भी अगर आप लोगों का कुछ हो गया होगा, हर्माइट लीजेंडर, एसोसिएटेड लीजेंडर
Yes sir, we
एटसेट्रा,
have
देन
tried it.
so we shall discuss those tomorrow. Okay?
Yes sir.
सर टुमारो क्लास होगा?
सर कल 4 से 6 होगा।
4 से 6
ओके
इसको
सर।
खत्म कर लेते हैं ना जल्दी, तो आप एग्जाम के लिए कोशिश प्रिपेयर
हाँ
करोगे।
सर।
ठीक है, थैंक यू।
सर
अब
वो सब खत्म होने के
इफ
बाद थोड़ा लास्ट क्लास को वो
डाउट क्लियरिंग कर देंगे, आपका जितना
सर सब
हमें
खत्म होने
असाइन।
के बाद लास्ट क्लास को वो एससीक्यू। हाँ
हाँ हाँ हाँ, आपका जितना मुझे दिया गया है शायद
वो जो
8।
एससीक्यू है और टीक्यू थोड़ा डिस्कशन हो जाएगा।
ठीक है, ठीक है, ठीक है। थैंक यू।
थैंक यू सर।